Hi learners, welcome. In this video, I am going to explain valency bond theory of metal complexes in 3 simple steps. Okay, so that it will be useful for you to understand whether the given complex is a spin free or spin fed, paramagnetic, diamagnetic, shape of the complex. All these things you can determine based on the valency bond theory. Let us see what are those 3 simple steps. First step. First thing, when you're, I will take one example. I'll explain with one example. Hexaamine cobaltate 3. Okay. So first thing, you just find out the metal complex and notice what is the central atom. And the central atom here is cobalt. Okay. Then what you have to do? You have to find its oxidation number. Find oxidation number of central atom. First step, you have to find oxidation number of central atom or oxidation state of central atom. So what you have to do in this case, let's say X is oxidation state of central atom plus 6 multiplied by charge of the ammonia. Ammonia is a neutral ligand, so charge is 0, should be equated to charge of the metal complex, that is 3 plus. So X is equal to 3 plus, means in this complex cobalt is in plus 3 oxidation state. Okay. First you have to do this. Then what you have to do? You have to please write valency electronic configuration. In the first step, we are talking about metal atom in this case. So how can I write valence state electronic configuration of cobalt? I know that cobalt valence state electronic cobalt configuration is argon 3d7 4s2 4p0. But here in this complex cobalt is in plus 3 oxidation state. So how I get plus 3 oxidation state? First I have to remove electrons first from the valence state, that is 2 electrons from s orbital and 1 electron from d orbital. Then the configuration of this will be 3d, 1 electron lost from this, so 3d6, 4s0 and 4p0. So that's about first step. I completed. Next what you have to do is, you have to find out whether the ligand is a weak field ligand or a strong field ligand. First step we discussed about the metal. Next it is surrounded by the ligands. So you have to see whether the ligand is a weak field ligand or a strong field ligand. So there is a simple way to remember weak field ligands and strong field ligands. I discussed it in a separate video. Please watch that video to know in detail. And here I am going to explain briefly. If your ligand is a halogen, or if your ligand is having donor atoms like oxygen, sulfur, phosphorus, then you can say it is a weak field ligand. So it's easy to remember. And similarly, strong field ligand means general donor atom used to be either nitrogen or carbon. Okay, so now you say this one, you can say whether it is a weak field ligand or strong field ligand. In ammonia, nitrogen is a donor atom. Whenever you say nitrogen is a donor atom, it is a strong field ligand. So second step, ammonia is a strong field ligand. Okay, you understood that. Now what we have to do in third step, you have to write electronic configuration and electrons. If a ligand is weak field ligand, then you have to write as it is the electronic configuration of metal without any pairing. Okay, you need to pair up the electrons. And if it is a strong field ligand, you have to pair up the electrons opposite to Hund's rule. pair up the electrons. Okay, in this case, ammonia is a strong field ligand. In the third step, what you have to do? So, cobalt 3 electronic configuration is 3d6, 4s0 and 4p0. So 6 electrons we have. So actually how I should write? I should write like this. This is the way of arranging electrons according to Hund's rule. But in this complex, how the cobalt 3 will be? Because of the strong field ligand, these electrons undergo pairing. Okay, first they will pair up two electrons each, then only they undergo hybridization. So how I should write now? Cobalt 3 in the metal complexes. Cobalt 3 in free state, it should be like this. But in this complex, because of the strong field ligand, electrons undergo pairing in this way. And it has 2 empty d orbitals now. And how many ligands we have in this complex? We have 6 ligands. And we need 6 empty orbitals. See, 1, 2, 3, 4, 5, 6. We got 6 empty orbitals. So these 6 empty orbitals in the central atom undergoes hybridization. What are these 2 orbitals? D, 2 d orbitals, 1 s orbital and 3 p orbitals. So it is undergoing d2sp3 hybridization. Next, you have to fill 6 lone pairs. So these 6 orbitals, hybrid orbitals, will be occupied by 6 electron pairs given by the 6 ammonia ligands. Okay, so this is the way of filling electrons in complex. Okay, from where we got this 6 electron pairs? From 6 ammonia ligands. Each ligand will donate a pair of electrons. Now what conclusions we can give based on this theory? You see, it is undergoing d2sp3 hybridization. Means the shape of the molecule, complex, is octahedral. Moreover, here d orbital is inner d, means 3d, it's not 4d. So you can say it is inner orbital octahedral complex. Inner orbital octahedral complex. And because of the strong field, all the electrons are undergoing pairing. There is no spin free electron here. So you can say the complex is low spin complex. Complex is low spin complex. As well as, if you see here, it is spin paired because all electrons are undergoing pairing. So we can say it's a spin paired complex. And there is no free electron in this complex. So you can say it is a diamagnetic in nature. All these points you can discuss based on valency bond theory. So simply if you follow these 3 steps, you can find hybridization as well as all these properties of metal complexes. Understand? So hope you guys understood this topic. Please subscribe to my channel. Thank you for watching.